Suppose a cereal manufacturer puts pictures of famous NFL athletes on cards in boxes of cereals, almost like a trading card or a sports card. The manufacturer announces that 25% of the boxes contain a picture of Travis Kelce, 35% a picture of Tyreek Hill, and the rest a picture of Joe Burrow. What's the probability of each of these? Okay, so let's use what we know. Find a picture of Travis Kelce in the first box you open. Well, this should be pretty easy. It's just 25% chance that Travis Kelce's on there, so it's 0.25. Done. Probably don't find a picture of Travis Kelce until the second box you open. So, the first box is anything else. So what is that? 0.75. Second box is Travis Kelce. 0.25. Multiply those together, and we'll get our probability. Which happens to be 0.1875. All right. Let's say you don't find a picture of Travis Kelce until the third box. All right. So not Travis Kelce, not Travis Kelce, then Travis Kelce. Okay. And if you multiply those two together, or sorry, those three, you get 0.14. We'll just say 1406. It's rounding a little bit. Let's say you don't find a picture of Travis Kelce until the sixth box. So same deal. It ends up being 0.75. We're going to say 5 of them, and then 0.25. And you get, I got 0.0593. Last question. You don't find a picture of Travis Kelce until the nth box. Now, think about this. Every one we did, the sixth box ended up being 0.75 to the fifth power times 0.25. The third box ended up being 0.75 to the second power, so one less than that, times 0.25. So all of these are getting the probability not 0.8, sorry, 0.75, whatever's not, to the n minus 1 power, and then multiplying by 0.25. That would be my formula for this particular situation. Not happening until a certain point. Now, this is actually getting us into a geometric situation. So geometric distributions is section 6.3d. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. Okay? We're going until we get a success. So on each trial, the probability of P of success must remain the same. Now, to determine if you have a geometric setting, we have a different, it's not the same as binomial with tins. It's very similar. It is TINC. Nice, lovely acronym. TINC stands for two outcomes again. So again, it has to be two outcomes. I, again, independent trials. N, no change in probability. But instead of a set number of trials, the K stands for keep going until a success. So if these conditions are met, the random variable would be geometric. And we would say, so we'll say if these are met, the random variable x could equal the number of trials till the first success. So that random variable is geometric. Oop, that got a little funky there. Sorry about that. Geometric with P equaling blank, and there's no set n. All right, we have no set number of trials. We just go until there's a success. And that's what makes it a geometric situation. So let's look at some geometric situations. Before we get into any other scenarios, I want to look at a couple things about them. Okay? If I know it's geometric, if I went through Tink and I realized it is geometric, I'm going to say X is the number of trials it takes to get a success. I'm going to state that it's geometric. And I'm going to state what P is, what Q is, and what X is. So if we're looking for a specific, like within a certain number of trials, or specifically at the 6th time, we want to know what the probability of getting success, that's the situation. Ultimately, if it is considered a discrete probability, if we were to write it out, we could say we have the probability of X at 1, 2, 3, all the way to infinity, which means it's always going to be skewed right. We'll get into that in a second, because it's always going to be continuing on to the right forever. But a couple notes. There is a formula for this, which is kind of like what we just did. The probability that X is equal to a certain X value is Q to the X minus 1 power times that one other one is P. So failures, and then our final one is a success. So success has to happen on the last one that we're looking for. Okay? There is no probability at 0. It doesn't make sense. It is considered discrete because you could have individual values here. So let's look at this example. Same situation. Let's say, what's the probability that you don't find a picture of Tyreek Hill until the 10th box you open? Now, if you know me, I don't want to write out 0.75 times 0.75 over and over again. I'm going to use this formula. But before I get to there, anytime we have an FRQ, anytime we have anything where it's work required, we want to state what we're looking at. So X, is the number of boxes to get a Hill picture. Oh, now we're looking at Tyreek Hill. A Hill card. Okay? This is geometric because we're going until it's not a set number of trials, so it's just geometric. And we have X, well, backtrack. We have P is, what is Hill? 0.35. Q is anything else, which is 0.65. And X is going to be 10 for this one. So what we can do is we can say the probability that X equals 10 would be fail 9 times, which would be 0.65 to the 9th power times success on that last one, on the 10th one, which is one of those. Okay, I'm not going to do 10 of those, I'm just going to do one of those. That total, it makes up 10. And I can find that probability and say that's the chance that I have that I find one exactly on the 10th box. And it's a 0.00725. So it's really a small chance that that'll happen. It's more likely that'll happen sooner than that. All right? That's the basic idea of geometric. There is a calculator function to help you out with that, but it's going to be more helpful to know the calculator function that deals with questions like this. What's the probability that you find a Travis Kelce picture among the first 7 boxes that you open? I'm going to slide these down and add that back in here. All right, so there it is back here. So find a picture of Travis Kelce among the first 7 boxes. So now we're not saying exactly at the 7th box. It's anywhere. It could be the first, could be the second, could be the third, could be the fourth, could be the 5th. Now, I don't know about you, but I don't want to add up all of those. Okay, this is going to be the same situation as before. We're trying to find a Travis Kelce. This is geometric. But, actually, let's just keep with Hill. We'll just make sure this is still Hill. Instead of Travis Kelce, we'll stick with Hill because we used that for the last one. But I don't want to add up all those values. So X could be any of 1 through 7. How helpful is that? So there's a function for that. There is a calculator function called Geomet CDF. This is a cumulative one because it could be anywhere through 1 through 7. In Geomet CDF, and I'm going to pull that up now, but in Geomet CDF, you need the probability and the value we're looking for. Okay? So let's go to second vars, all the way down to the bottom, Geomet CDF. All you need is the probability of success, which we said the probability that we'll get a Tyreek Hill was 0.35, right? We want to get it within the first 7, so that's going to be my X value. It's, again, kind of like binom CDF. It's the highest, the last value, so everything this and below. We're going to paste that here. We got 0.950, let's say 0.951, okay? But all we're putting in there is 0.35 for Tyreek Hill, and we want it within the first 7, okay? And again, that was 0.951. And like binom CDF, things are going to work very similar with Geomet CDF. So what's the probability of finding a picture of Tyreek Hill among the first 4? All right, same idea, 1 through 4. We're going to do Geomet CDF. By the way, if we're using this, we still want to list all of our things. In this case, we're doing 1 through 4. But it is just going to be 0.35 and 4. Calculator does the rest. I'm actually just going to copy this thing back over here, and I'm just going to change this to a 4. I get 0.821, we'll say. Now, what happens when you get a question like this? What's the probability that you won't find a picture of Tyreek Hill among the first 7 boxes you open? Well, if you think about our probability distribution, it has to happen, like it has to be at least 1, but it could go on forever into infinity. But still, all of these have to add up to 1. All of the probabilities still have to add up to 1. So we don't have an ending value. We just say we don't want it to happen in the first 7. So if we found the probability of the first 7, we could just subtract it from 1. So basically our X is anywhere from 8 to infinity. So what we're going to do is take 1 minus Geomet CDF. We'll use 0.35, right? 0.35. And we don't want it within the first 7. So we're just going to subtract that from 1. And that'll give us our probability. We want it 8 or after. So all I have to do, I did first 7 in that first one. So it was minus 0.951. So 1 minus 0.951 will get us my answer here, which is 0.049. All right, I've got one last question here. What's the probability that you won't find a picture of Joe Burrow among the first 12 boxes of cereal you open? So I want to point out that this is a great way to do it, that we're recognizing that it's geometric, and we're looking for, this time we're going to look for, what is it, 12 to infinity. And this is for Joe Burrow. I'm just going to change this. We'll change it back to Hill, just so using the same probabilities. But we can use the geometric where it's still the same idea. We'd be doing 1 minus Geomet CDF. and we have the probability of 0.35, and we don't want it in the first 12, we want 13 and after, so we're going to subtract the first 12. And if we do that, we'd get a probability. I'll pull this up just so you can see it. It'd be 1 minus, oops, I'm just going to put in 12 here. We'll do 1 minus that. So it would be 0.00569, we'll say. But that's not the only way, and this is what I've had people ask. How do I know what distribution to use? Well, you could theoretically take like just probability rules. So this is Geomet CDF. We could use probability rules. Just knowing that it's got to be a fail 12 times in a row, which would be a fail for this would be 0.65 12 times in a row. The chance of it being a fail 12 times in a row just so happens to be 0.00569. So you get the same answer, just a different way. We can use probability rules with these because it's a very similar situation. We could also change this and say it's binomial because it's either Tyreek Hill or not. So we could say that it's binomial. We would just have n is 12. X is 0. We have 0 successes in the first 12. The probability was 0.35. Whoops. Q would be 0.65. So you could say, theoretically, 12 choose 0. We don't want any successes in the first 12. Times 0.35 to the 0 times 0.65 to everything else. Which gets you, you'll never guess it, 0.00569. All right, there are multiple ways to do this. It depends on how you're looking at it. All right. Now, last thing I want to talk about with these geometric situations, though, is what's true about, like, if we ever asked to describe the distribution. Again, these are just all theoretical. We don't actually have the data. But I want to point out a couple things about shape, center, and variability. The shape. I mentioned it before, but because it starts at 1 and then it could keep going on forever, the probability is going to get smaller and smaller. This is always skewed right. Always. If we have a geometric situation, it is always skewed right. Measure of center. Now these I have a couple formulas for you. I'm not going to talk about how we derive them, but they are also on your formula sheet. If it's geometric and you want to find the mean, it is 1 divided by p. That is it. And then we can explain it the same way we have before. Measure of variability. Standard deviation. There's a formula for that. It is the square root of q, or 1 minus p, as it says on your formula sheet, divided by p. There's your formula for variability. All right? So if we're taking a look at a scenario which we've actually looked at before, where it says people with O-negative blood are called universal donors because O-neg can be given to anybody else regardless of their blood type. Only about 6% of people have O-negative blood. Describe the distribution of X, where X is how many people examined before you find someone with O-neg blood. So first of all, I would make sure you go through and check what type of distribution it is. In this case, you're going until you get someone, so you think it's going to be geometric. We need to verify that. It's either O blood or not. So it is 2 options. Independent, we'll say there is no effect on others. Everyone's a separate. I think that you can't say one person's blood type affects someone else. No change in probability, it's just 0.06. Keep going until you get 0. Yes. So we have checked all 4 boxes. And we can say, because of that, the distribution of number of people examined to find O neg blood is geometric with p equals 0.06. Now I'm going to keep going because now if we know it's geometric, we can say the shape is skewed right. With a mean of, ends up being 16.67 people. How did I get that? I did 1 divided by 0.06. And a standard deviation of 16.16 people. How did I get that? I did the square root of 0.94, the square root of q, divided by p, which is 0.06. Done. I just described the distribution. So very similar to geometric, but we got binomial, a couple different formulas though. I forgot to mention though, last thing, do we need to deal with the measure of any outliers? No. It's going to be skewed right, so that's just going to be the nature of the shape. And we can say if our probability is unusual, just like we have in the past. But that's what I wanted to get to with geometric settings or geometric distributions. Similar, but one main thing that's different from binomial is that you keep going until you get a success. So that's section 6.3d, the end of probability distributions in this chapter. So we'll see you next time.